For this lesson, we're going to cover stoichiometry of chemical reactions. It can be challenging for students sometimes, but the general principles of unit conversions follow with the stoichiometric relationships as well. So basically, we look at the coefficients that are in the chemical equation, and they're what go into the conversion tables. Rather than the other quantities we've used before. So we relate moles to moles and grams to moles, moles to grams. So let's have a look at some examples of that and how to work the problems. Here's the screen shared. So let's have a look at our first reaction. We've got one mole of S reacts with 3 moles of Cl2. And so as I stated before, in our conversion tables before, we may have been relating, say, kilograms to grams or kilograms to pounds or something like that. So here we're just dealing with moles to moles in this first question. But the relationship is how many of these sulfurs are going to react with a given quantity of Cl2, and that ratio is 1:3. So for every 1 sulfur, we would need 3 Cl2s. Okay, so let's set this up as a problem. So how many moles of Cl2 are required to react completely with 1.65 moles of sulfur solid? So I'll put this here. Okay, as a first step. And I'm going to have my 1.65 mole of sulfur. Okay, and so then that will react with some amount of chlorine. Now, here's where we put in that stoichiometric ratio. So the stoichiometric ratio is a fancy word for just saying these numbers that are in front of these quantities in the equation. So if we start off with mole of sulfur in the numerator there, I know I've got to have mole of sulfur in the denominator over here. So straight away I can put in that I'm going to have mole of sulfur. Because I'm trying to relate it to the chlorine here, the Cl2, that's when I look at the mole ratio. I've got 1 mole of sulfur goes with 3 mole of Cl2. Simply from what's in that equation here. So I know I'm deliberating on this, but it's important to understand where we're at this point. So if I just stop here and just crossed off the units, I'm not going to, but if I did just cross off the units here, we'd see that we're currently in moles of Cl2. Okay. So mole of Cl2 is all we need to get to, because that's what the question has asked, how many moles of Cl2. Let's just say it did ask for the grams of Cl2. Then I would just have an additional step here relating 1 mole of Cl2 into the mass of the Cl2. So that would be a final step there. But we don't need this final step in this particular question. But further down, we'll see in question 2, we're going to be dealing with grams rather than just purely on a mole basis. I don't have to go any further. And why I'm emphasizing that is it's important to understand what the questions are asking. So we're asking just to work out the moles of Cl2. Sometimes students get lost as to where they're at, but this part here is the central part. And that process here, when we carry it on further down, we can see that central relationship between one quantity in moles to another quantity in moles will be at the heart of all these calculations. Okay, so I'm just going to delete that one, and we can just work it out. So on the calculator, I'm just going to put 1.65 times 3, and I get 4.95. Mole. And with these ones, it's a good idea to put in the actual species you're looking at. I say that because sometimes if you just put 4.95 mole, because there are a lot of different numbers floating around, different quantities, it may not be clear mole of what, you see. Okay, so now we're looking at 0.564 mole of sulfur and 1.35 mole of Cl2 are reacted, and one of them is going to be limiting. So what it means by the limiting is that with this equation up here, this is an equation where you would have everything ideal, 1 mole of sulfur for 3 moles of Cl2, and away it goes in the reaction. But in reality, there may be too many moles of sulfur, or there may be too many moles of Cl2 relative to the stoichiometric ratio. And so, so the one that's in excess is called the excess reagent, and the one that is not enough for the full reaction to occur is called the limiting reagent. Okay, so the way we set this up is I'm just going to go through and work out the actual number of moles of this SCl6 we're going to get. And whichever method gives me the most SCl6 is reagent that's in excess, and the one that gives me the least amount of SCl6 is the one that's limiting. Okay. There is another way that we could look at this, but I'm just going to do it this way for the time being, just to reinforce these conversions. Okay, so I'm going to take this to the product. So I'm going to relate this to the product. So why 1 mole of S? Because here is where I relate the numbers, the stoichiometric numbers. And we can see from that relationship that it's a 1-to-1 relationship. Okay. So that was reasonably straightforward. But again, I'm sort of emphasizing the process here. We can see that 1 mole of sulfur goes to 1 mole of Cl6. So of course it makes sense that if we had 0.564 moles of sulfur, we're just going to get 0.564 moles of the SCl6. Let's repeat the process with the chlorine, and that's a little bit different because we've got the 3 moles here. Okay. So we start at 1.35 mole of the Cl2. And again, I'm trying to relate this back to the product. So what does that look like? In the same way that when I was looking at the sulfur, I was considering the stoichiometric ratio between the sulfur and the SCl6. I'm now going to look at the stoichiometric ratio between the Cl2 and the SCl6. So this time down the bottom, I'm going to have 3 moles of the Cl2 and 1 moles of the SCl6. Okay, and again, these 1s and 3s just come from here. Okay. So now, a third of 1.35 is 0.45. Now, what these calculations show is that based upon 0.564 moles of sulfur, I could form this many moles, again, 0.564, of SCl6, provided there was enough Cl2, or if there's excess Cl2. That's how many moles of SCl6 I would get. Again, as long as there's enough Cl2 to let that happen. And similarly, based off 1.35 moles of Cl2, I can form 0.45 moles of SCl6. Okay. Again, provided I've got enough sulfur to support that. So let's have a look at another analogy with this. And the text uses cheese sandwiches as an analogy. A simple budget cheese sandwich would be 2 slices of bread, 1 slice of cheese. Okay. So that'd be very, very plain cheese sandwich. 2 slices of bread, 1 slice of cheese. If I had 50 slices of bread and 25 slices of cheese, then I could make 25 cheese sandwiches because there's 2 pieces of bread for 1 piece of cheese. And so 50 slices of bread, 25 slices of cheese would support 25 cheese sandwiches. Now, if there were 100 slices of bread, but still only 25 slices of cheese, then you're still only going to be able to form 25 cheese sandwiches. You would just have an excess of 50 slices of bread, if that makes sense. So that's exactly what we're looking at here. So again, we'll go back to the original question, and it's trying to see which one's going to be the limiting. So the fact that only 0.45 moles of SCl6 is formed with the Cl2 means that the Cl2 is limiting. Okay, so it's limiting. If I adjusted these numbers, for instance, and had 1.8 mole of Cl2, then if I read the calculation, 1.8 mole of Cl2, this would become 0.6. Okay, it'd become 0.6. So in that case, then 0.6 would exceed the 0.564, and then that would mean that Cl2 would then be in excess because I would have enough Cl2 to form the extra amount of SCl6. But as it stands, we just have our 1.35 mole of Cl2. And so that means that I can make this statement: the Cl2 gas is limiting. Okay. So this one, I'll just backtrack a little bit. I could have already seen, without having to do these calculations, I could have actually already seen that the Cl2 was going to be limiting. And the reason is because looking at the original equation, I've got 1:3. I'll always need 3 times as much Cl2 as what I have sulfur. And so realistically, for the balance, it would have been 3 times this number, which would have been 1.692. So if I have 1.692 mole of Cl2, then it would have been the correct ratio. So that's another way you could sort of do it. I don't know if that's clear or not, but basically I need 3 times this number of Cl2 because the original equation says I have 3 times the Cl2 requirement as sulfur. Okay, so that's another way to do it. These questions B and C often go in tandem. So if you do the calculation like I did here, and again, we were just getting extra practice on how to do these conversions, it automatically sets you up for C. Because C is saying how many moles of Cl6 be formed if we have the 1.65 moles of Cl2 reacting with excess. Well, then I can follow this same methodology and put it in pretty simply without having to think too much about it. So I put in, I know I've got excess S now, so S is not going to be limiting and it is more than enough S. So I would just do the same calculation as what I did here, but instead of having 1.35, it'll be 1.65. Okay. And so that's going to equal 1.65 divided by 3, which is 0.55. And I'm going to make it 0.550 because we want our significant figures to match. And that's the answer for that. Again, if you've worked out this way, and often when you go from here to here, they may just say, the same number as 1.35 or something like that. So in which case you just report the number straight down. Okay. So hopefully that makes sense. And notice how I've used the significant figures. These 3s and 1s here aren't factored into the significant figures because they're exact numbers. So there's exactly 1:3 ratio. So significant figures are just based on the quantities we're given, which in all these problems happen to be 3. So when I'm my answers, I try and make sure that I match that to the 3 significant figures. So this problem 2A is going, well, before I even do 2A, let's balance the equation. So when balancing the equation, you want to go back and forth a bit to sort of try and add up. So what I do is I try and add up the things on the left. So how many potassiums on the left? 1. How many on the right? 1. That balances so far. How many H's on the left? 2. How many H's on the right? Well, there's 1, plus 2 is 3. So we have a problem there. So often we just like to put a 2 in front to get us going. Sometimes, it can be trial and error, and you may have to change values or something. But for the time being, we'll put a 2 there and see how that goes. Okay, and so if I put a 2 there, now I'll look at what I've got, and I've got 4 hydrogens on the left, and now I've got 3 still on the right. So the way to balance that out would be to put a 2 at the front. So how does that look? That looks good for the H's. 4 and 4, because remember, this 2 multiplies through everything. Let's have a look at our O's. 2 O's. That 2 multiplies through everything. 2 O's, so that's good. That matches left and right. But then we need to go back and have a look at our potassium. So 1 potassium on the left, 2 on the right. Okay, there's 2 on the right there. So we need to put a 2 in front here, and then that should be good to balance. Okay, so we had 2 potassium, and this really should have had a solid at the front there. So I might correct that. Well, it's not that important. But yeah, there should be an S there for solid. Okay. Now we're looking at grams. So the previous question 1, we're dealing just mole to mole. But now we're starting with grams. And and we can report to grams as well. For 2A, you wouldn't actually have to report to grams. You could just compare mole to mole. But we'll report it out in grams to show the process. So like all these conversion factors or conversion problems, we start with what we have in the question, which is 22 grams potassium. Okay. Then we have our first thing here. So 22 grams potassium means that we've got to have what bottom? Grams of potassium. So that's, even if I'm not really quite sure what I'm doing, I always just start with that. I know that I've got to have grams of potassium on the bottom, because it has to cancel, and that can often job me into knowing what I'm doing. So if I've got those grams of potassium, now what I have to do is to think about what I need to do to relate one quantity to another. I can't relate a gram to a gram in the case of a chemical reaction. And the reason you can't is because if we look at the equation, when we're relating the potassium to the water, these aren't on gram to gram relationships. They're on mole to mole relationships. They're from a molecule to molecule, which is the same as a mole to mole, because that Avogadro's number applies 6.022 by 10 to the 23. It's applied evenly across. So we can talk about it in terms of moles, because moles gives us a nice convenient mass quantity to deal with. And so looking at our mole to mole or molecule to molecule, even if you went right down that level, means that we can't relate grams to grams directly. So we're going to want to convert into our moles. So when I do that, I would be looking at some quantity of grams that's going to go into the moles of potassium. So when I look at my periodic table, I see here that, so I've got one here. I see that potassium is 39.10 grams per mole. So I make sure I look at that. There's 39.10 grams of potassium is related to 1 mole of potassium. Okay. So now, if I just stopped the calculation there, I would actually be in units of moles of potassium because my grams of potassium are crossing off. And that's important because I need to be in the moles, like I said, in order to relate that chemical equation. And now that I am in grams, or in moles of potassium, I can use that equation to now look. And so looking back at the question and looking at my strategy I used above, I'm going to take this just through to the products. I'm going to take it through the products and just see what I end up with as far as a product quantity. Okay, so I'm going to relate this reactant straight through to a product, and I can choose either one actually. I'll just choose the H2. I guess it wouldn't really matter which one I use. But we'll just use the H2 for argument's sake. So my ratio of potassium to H2 is going to be 2:1. So 2 moles of potassium is equivalent to 1 mole of the H2. Okay, again, this part here is central. That's central to all these problems in the same way up here. That part was there, that part was there, and they're relating these mole ratios to come from the equation themselves. We've had to use another step at this point. So at the start, we had to go from our grams into mole, then mole to mole, and then here we can go mole to grams. So if we wanted to, we could leave it here and work out in our units at the moment are moles of H2, and so I could work out the moles of H2 there. I could repeat this same problem with 15 grams of water. So I go 15 grams of water, convert that into moles of water, then relate the moles of water to the moles of H2. And so I compare a mole of H2 by the two different masses. Just for argument's sake, I'm just going to convert grams to grams because we need a bit of practice with that. So my next step would be relating these moles of H2 into grams of H2. Okay, so one mole of H2, how many grams is that going to be? Well, it's again going to be related to the molar mass. And so if a single H is 1.008 grams per mole, then I've got 2 of those for an H2. So 2 times 1.008 is 2.016. So I've got 2.016 grams of H2. And so I put all this into the calculator. So I've got 22 divided by 39.1 divide by the 2 because there's a 2 here. And then multiplied by the 2.016. And I'll get an answer of 0.567. But we want two significant figures anyway, so that would just be 0.57. Okay. And we've just chosen H2. Like I said, we could have done this calculation for potassium hydroxide instead, the KO8. But anyway, we chose the H2. Now I'm going to repeat the exact same process, but with the H2O. So as the question states, I have 15 grams of my H2O. And this is to be G, not H. 15 grams of H2O. And then I'm going to relate my grams of H2O. And so the molar mass of H2O, when I go to my periodic table and look at it, for the H is 1.008, and then the oxygen is 16, gives me an 18 0.02 roughly, or a 0.16 grams. If we can squeeze this in here. Yeah, it's off a little bit. So 18.016 grams of H2O would be equivalent to 1 mole of H2O. Whoops. Not sure what it's doing, what it's doing, but okay, here we go. And then I look at my stoichiometric ratio. So from here, it's 2 moles of H2O, gives us 1 mole of the water again. Sorry, of the H2 gas again. Okay, and so then the last step would be to convert to grams. So again, this part's exactly the same as what it was in the previous calculation. And so we would have our 1 mole of H2 is the same as 2.016 grams of H2. And I didn't put this in when I should have. Okay. And so we end up with 15 times 0.016 divided by 18.016 divided by 2. Okay, we get 0.84 grams of H2. Okay. So, we can see that the 22 grams of potassium actually produces less H2 gas, which again, that's why even though potassium is actually in a larger quantity mass-wise, it's in a smaller quantity moles-wise, which is to be expected. The molar mass of potassium is 39.1. The molar mass of the water is much less at 18.016. So because the molar mass of the water is less, relatively speaking, you can generate more moles for a given mass, if that makes sense. So our 22 grams of potassium, we produced our 0.57 grams of H2, whereas the 15 grams of water is 0.84 grams of H2. So the limiting reagent is going to be our potassium. So I can just put that here. Okay. Now, just to refresh, that means that the water is our excess reactant. Okay, so if the reaction did not go to completion and 0.12 grams of H2 formed, what is the percent yield? So luckily we did choose the H2 quantity here, and that's why it's often good to read ahead. If I had have worked it out for potassium hydroxide instead, then we would have had different numbers here, of course. And basically, it would have been a similar calculation. It's just that when I'm relating 2 moles of potassium, I would have then had 2 moles of potassium hydroxide because there's a 2 and a 2 in the equation here. And then I would have used 1 mole of potassium hydroxide and the molar mass of potassium hydroxide and got a number. We still would have had a lower number via the calculation on the left versus the calculation on the right, but we would have had different numbers because we were calculating the masses of potassium hydroxide. At any rate, we chose the hydrogen. So given that we've got the hydrogen, that's already part of our work done for us for this question. Because what B's asking is if we only form 0.12 grams of hydrogen, how does that compare to what we would have expected to form? So how much would we have expected to form if it went to completion? We would have expected the 0.57, okay? Because we had enough potassium to support 0.57 grams of hydrogen. We had enough water to support 0.84 grams. But just because we had enough water to support the 0.84 grams doesn't mean we get 0.84 grams because we had a limiting amount of potassium. In the same way, when we're talking about the cheese sandwiches, even though we might have had 100 slices of bread, which would support 50 cheese sandwiches, if we only have 25 slices of cheese, we can only have 25 cheese sandwiches. So here we have to compare the 0.57 to the 0.12. So our formula for the percent yield is going to be equal to our actual divided by our theoretical. I'll just leave it at actual. I won't put in grams yet because I want to make a statement on that actually. So it's just actual divided by theoretical. There we go. Then we want to multiply that by our 100%. Okay. And so in this particular case, we have our 0.12 grams of H2. And then we're going to divide that by what we would have expected to get if it was going to be a proper yield. Or sorry, not a proper yield, but a complete yield. Okay. Multiplied by so we'll put that in the calculator in a second. And when we do, we're going to get 21%. That's our percent yield is 21%. So always actual divided by theoretical, but you've got to make sure that it's going to be the same quantities. It's the same units. So In B, we were given 0.12 grams of H2. So I need to compare it to what the full yield would be if it went to completion, which must be also in grams. If it was calculated just in mole, then I'd have to convert the mole to the grams. I've got to compare apples to apples. Or I could alternatively convert the grams back to mole. So if I'd worked out previously that it was, let's say 5 moles of H2, and I'm given this quantity of grams, then I could convert the grams to their mole equivalent of H2, just using that conversion process. Or convert the mole of H2 into the grams. But either way, it's got to be the same units, actual theoretical. It doesn't have to be grams. You could have both moles, but as long as they're the same, you're okay. And so that concludes our lesson on the stoichiometry. The main thing is you take it very systematically as you go through, very orderly, and remember that central, in the middle of all these, is going to have to relate moles to moles via the stoichiometry in the equation. So you might go grams to mole to mole, and then moles to grams, okay? Or you could just have the problem in moles, and then it's just a mole to mole, mole to mole. But but usually you'll often have it grams to mole to mole, relating through the equation, the stoichiometry, and then moles to grams, usually calculating the product. Okay. Best of luck with it. And again, persistency is the major key with these reactions and working out how the mathematics is going to work.